Hello dear students, in the last video we discussed about variation of conductance, conductivity, molar conductivity with the dilution, and after that we also learned about Kohlrausch law and its applications. And in today's class, that is lecture number 17, we'll start with Kohlrausch law's problems. But before we'll going to start Kohlrausch law's problems, once again we'll recall limiting molar conductivity. See here, the definition of limiting molar conductivity is the molar conductance of an electrolyte. The molar conductance of an electrolyte at infinite dilution or zero concentration is called as limiting molar conductivity. The molar conductance of an electrolyte at infinite dilution or zero concentration is called as limiting molar conductivity, and it is designated with lambda m naught or lambda m infinite. Next, one more concept is left, that is solubility and solubility product of any sparingly soluble salt. We will see the relation there. Sparingly soluble salt is nothing but partially soluble salt. Right. Regarding sparingly soluble salts, already we have learned in our first year equilibrium topic. Right. Now, saturated solution of sparingly soluble salt can be considered as at infinite dilution only. I'll repeat. Saturated solution we have reached means it is at infinite dilution only. Therefore, at infinite dilution, whatever the molar conductivity is there, nothing but limiting molar conductivity. Lambda m we can replace with the lambda m naught. And molar solubility, nothing but molarity also we can replace with the S symbol. Therefore, our molar conductivity formula lambda m or lambda m naught is equals to K into 1000 by S. Nothing but m, both are same only. I need a solubility formula, that's why I have replaced with the S symbol. Therefore, if you interchange the terms, S is equals to K into 1000 by lambda m naught. Then from this formula we'll get solubility value. From that solubility we can calculate solubility product value also. Right. Next we'll start problems based on Kohlrausch law. Right. The first question of Kohlrausch law problem, first question is like this. Question number 1. Given lambda naught HCl is equals to 426 Simon centimeter square per mole. Lambda naught NaCl value has given 126 Simon centimeter square per mole, and a lambda naught CH3COONA value 91 Simon centimeter square per mole. Calculate lambda m naught of CH3COOH is the question. That's it. Here HCl limiting molar conductance has given, as well as NaCl limiting molar conductance has given, as well as sodium acetate limiting molar conductance also has given. All three are strong electrolytes. Strong electrolytes limiting molar conductance can be calculated by graphical study, nothing but experimental studies. But he has asked the question limiting a molar conductance of acetic acid. Acetic acid is absolutely weak electrolyte. Okay, for a weak electrolyte we cannot calculate from graphical study. That's why we have to use these three strong electrolytes. Now, these three strong electrolytes we have to arrange in a systematic manner. We'll see its solution formula. Answer: lambda m naught acetic acid is equals to. Now, how to arrange all three electrolytes? Regarding this, in last video we have discussed about applications of Kohlrausch law. In that, one of the applications we have discussed, that is indirect method. See here once again, CH3COOH, if you split you will get a CH3CO minus as well as H plus. First we have to select where acetate ion, where CH3COO minus ion is present. Right, CH3COO minus ion is present here. So I will write this symbol here first. Lambda naught CH3COO Na. Next plus, where H plus ion is present we have to identify. H plus ion is present in HCl. Next we will write this symbol lambda naught HCl. Next, CH3COO minus and H plus only needed. Na plus Cl minus not needed. That's why next immediately we have to write minus lambda naught. Remaining is NaCl. NaCl will write by doing the subtraction because NaCl we have to remove them. Now we'll just substitute the values. Sodium acetate value. Sodium acetate value is already given 91. Plus HCl value also already given 426 minus NaCl value is 126. Again if you simplify you will get 391 Simon centimeter square per mole. That's it. 391 Simon centimeter square per mole. This is limiting the molar conductance of acetic acid. Weak electrolyte limiting molar conductance we have calculated like this. Right. Next question. Next we'll go to second question, that is lambda m naught values of NaCl and KCl are found to be 126.5 and 149.9 Simon centimeter square per mole. The ionic conductance of Na plus ion at infinite dilution is 50.1 Simon centimeter square per mole. Calculate ionic conductance of K plus ion at infinite dilution. That's it. This is the question. First, we'll try to understand the given data. Lambda m naught, nothing but a limiting molar conductance of NaCl as well as KCl. Of course, both are strong electrolytes. Both limiting molar conductance values has already given the question. At the same time, the ionic conductance of Na plus ion also. The ionic conductance of Na plus ion also has given at infinite dilution. Nothing but limiting molar conductance of Na plus also given, and is asking a limiting molar conductance of K plus. Right. Here first we'll write the given data. That is answer. Lambda naught NaCl value has given, that is 126.5. Units are Simon centimeter square per mole, and lambda naught KCl value is equals to 149.9 Simon centimeter square per mole. At the same time, lambda naught Na plus also given, that is equals to 50.1. Of course, the same units, and asking a lambda naught K plus is question mark. Then how to get K plus we'll see now. First, what I am doing here NaCl value is available as well as Na plus value is also available. NaCl N plus. Therefore, we will write like this: lambda naught NaCl is equals to lambda naught Na plus lambda naught Cl minus. We can write like that. Now here NaCl value is available as well as Na plus value is also available. Cl minus is not known. Therefore, we will bring lambda naught Cl minus LHS is equals to lambda naught NaCl minus lambda naught Na plus. That's it. Therefore, we'll just substitute the values. NaCl value is already given in the question. 126.5 minus lambda naught Na plus value is 50.1. And if you do subtraction, you will get 76.4 Simon centimeter square per mole. Of course, this is not our answer. Just a Cl minus value only obtained here, but we need a K plus value. Lambda naught K plus value is required. Therefore, once again we will write like this: lambda naught KCl is equals to lambda naught K plus lambda naught Cl minus. Now here lambda naught KCl is available. I mean, this value is known, as well as lambda naught Cl minus value is also known, but lambda naught K plus is not known. Therefore, lambda naught K plus bring HS is equals to lambda naught KCl minus lambda naught Cl minus. That's it. Therefore, if you substitute the values, KCl value is 149.1 minus Cl minus value just now calculated 76.4, and if you subtract, you will get 73.5 Simon centimeter square per mole. This is the limiting molar conductance of K plus. That's it. Once again, limiting molar conductance of NaCl as well as KCl as well as Na plus has given, and is asking limiting molar conductance of K plus. Therefore, here NaCl known as well as Na plus known. With the help of these two, we have calculated Cl minus. Next, KCl we can write like this. Here also KCl value is known as well as the Cl minus value is known. With the help of these two values, we can calculate K plus value also. This is the final answer. This is the final answer. Its value is 73.5. That's it. Next question. Yeah, next question we'll see. Molar conductivity of CH3COOH at some concentration was found to be 11.7 Simon centimeter square per mole if its limiting molar conductivity is 391 Simon centimeter square per mole. Calculate degree of ionization of CH3COOH. That's it. It's a question. Again, first we'll try to collect its data. Molar conductivity of acetic acid at some concentration. It is not a limiting molar conductivity. At some concentration, nothing but lambda MC was found to be 11.7. Some value is given, and it's a limiting molar conductivity. Nothing but at zero concentration. It is at some concentration, it is at a zero concentration. Its value is 391, and is asking a degree of ionization, nothing but alpha. In the last video, we discussed about Kohlrausch applications. There, one of the application is finding the alpha. Alpha we have to calculate. For that purpose, we will have direct formula, that is alpha is equals to lambda MC divided by lambda M naught. That's it. It is nothing but molar conductivity at a given concentration, nothing but at some concentration, okay, divided by lambda M naught, limiting molar conductivity. Therefore, we will just substitute the values. Lambda MC value is 11.7 divided by limiting molar conductivity value is 391, and if you do the simplification, you will get 0.03. 0.03 you will get. This is alpha value. And of course, if you suppose want to calculate a percentage of alpha, it is nothing but into 100. If you do, you will get a 3%. That's it. That's all. It is a direct formula. Lambda mc by lambda m naught. Molar conductance at a given concentration divided by molar conductance at a zero concentration. Nothing but infinite dilution. That's it. Next question. Next question is conductivity of a saturated solution of AgCl at 298 kelvins is found to be 1.328 into 10 to the power of minus 6 Simon per centimeter. Find its solubility. If ionic conductances of Ag plus and Cl minus at infinite dilution are 61.9 Simon centimeters per mole and 76.3 Simon centimeters per mole respectively. This is a question. Now, how to solve this question? Just we'll see then. Conductivity of saturated solution of AgCl. See here, AgCl is a sparingly soluble salt, and it's a saturated solution. Saturated solution reached nothing but it's limiting molar conductivity is reached, right? At a 298 kelvins, E is found to be 1.328 into 10 to minus 6. Nothing but it is K value because conductivity it is K. And find its solubility. Nothing but molar solubility. Nothing but molarity we have to calculate. And if ionic conductances of Ag plus and Cl minus at infinite dilution are Ag plus value is 61.9 and Cl minus value is 76.3. How to calculate we'll see now. Very simple. We'll have the formula lambda m naught. I am taking now because saturated solution nothing but lambda m naught is equals to K into 1000. Why? Because see here units CJ system. That's why we are using the CJ system related formula only. K into 1000 by m. Instead of m, we can replace with s because it is at a saturated solution, nothing but at infinite dilution only. Okay, this is our formula. But in this is asking S value, solubility is asking. That's why we'll interchange the terms. S is equals to K into 1000 divided by lambda m naught. Now in the question, K value already given. There is no doubt. 1000 is 1000 only, but lambda m naught of AgCl value has not given. Lambda m naught limiting molar conductance of AgCl has not given. For that purpose, he has given a hint nothing but indirectly he has given like this. Therefore, lambda m naught AgCl is equals to lambda m naught Ag plus lambda m naught Cl minus. Both values already given in the question. We'll just substitute them. One is a 61.9 plus another one is a 76.3. Again, if you add them, you will get 138.2 Simon centimeter square per mole. Of course, this is not answer. It is just lambda m naught we have calculated. It is nothing but lambda m naught. Limiting molar conductivity we have calculated. Then finally we will find solubility. solubility purpose, we'll substitute the values. S is equals to K. Conductivity value is 1.328. 1.328 into 10 to the power of minus 6 into 1000 divided by that is a solubility, nothing but a molar solubility, that is a 138.2, and if you will do simplification, S value you will get a 10 to the power of minus 5. Its units are mole per liter, nothing but a molar solubility is obtained. That's it. Molar solubility has calculated like this. Okay. Here AgCl, of course, is sparingly soluble salt, and is telling it's saturated solution. Saturated solution reached means it is reached infinite dilution stage only. Right. Then this is our formula. Lambda m I have replaced with the lambda m naught because reached at infinite dilution stage. And here m we can replace with s. We need s value. That's why we'll interchange the term. S is equals to k into 1000 by lambda m naught. K value already given in the question. Lambda m naught has not given, but given indirectly like this. Lambda m naught calculated like this. That is lambda m naught AgCl is equals to lambda m naught Ag plus Cl minus. If you substitute the values, you will get lambda m naught. Then finally, you will get solubility. Its units are mole per liter or molar. That's all. Next question we'll see now. Next question is like this. Ionic conductance at infinite dilution of Ca plus 2 and Cl minus are 119 and 76 Simon centimeter square per mole respectively. Calculate equivalent conductance of CaCl2 at infinite dilution. This is a question. First, we'll try to understand the question carefully. Ionic conductance at infinite dilution of Ca plus 2 and Cl minus ions are given 119 as well as 76 Simon centimeter square per mole respectively, and calculate equivalent conductance of CaCl2 is asking. Here I will have two methods. We'll see both the methods. Then method 1, first method will solve like this. First method, CaCl2, if it is a split, you will get a Ca plus 2 plus 2 Cl minus. Ca plus 2 plus 2 Cl minus ions. Therefore, lambda naught. I'll calculate molar conductance of calcium chloride. I'll calculate first of all. Of course, he's asking equivalent conductance. But first I'll calculate molar conductance. Lambda m naught CaCl2 is equals to lambda m naught Ca plus 2 plus 2 into lambda m naught Cl minus. This is molar conductance. That is equals to Ca plus 2. Ca plus 2 ionic conductance, nothing but molar conductance value is 119 plus 2 into Cl minus value is 76, and if you do the simplification value, you will get 271. Lambda naught calcium chloride is equals to 271 Simon centimeter square per mole. Now molar conductance of calcium chloride has calculated, but we don't need molar conductance, we need equivalent conductance. Therefore, in the last video we discussed about the relation between molar conductance and equivalent conductance. Based on that, here equivalent conductance purpose, lambda naught equivalent conductance of calcium chloride is equals to lambda naught molar conductance of calcium chloride divided by its valency. This is the formula. In the last video we derived this expression. Therefore lambda naught equivalent conductance of calcium chloride is equals to lambda naught molar conductance of calcium chloride value 271 divided by valency of calcium chloride. Just now we have taken here Ca plus 2 and 2Cl minus. Here 2 and 2. Valency is 2 divided by 2. If you do, then your answer is 135.5. 135.5 units are here. Simon centimeter square per equivalent. We have to write per equivalent. This is our answer. This is method 1. First, what we have calculated? Molar conductance we have calculated. That molar conductance we have converted into equivalent conductance just by dividing with valency. It is method 1. Or method 2 also will do now. Method 2. Second method purpose, directly I will solve like this. That is a lambda naught equivalent conductance of calcium chloride is equals to that is a 1 by or any electrolyte. We'll write the first formula. Lambda naught equivalent conductance of any electrolyte is equals to 1 by valency of lambda naught cation, right, cation C plus 1 by valency lambda naught anion. This is our formula. We'll get directly equivalent conductance. No need to go to molar conductance. Directly we'll get the equivalent conductance if you use this formula. 1 by valency means cation valency into cationic molar conductance plus anion valency into anionic molar conductance. Right. We'll substitute the values. There is nothing but lambda naught equivalent conductance of calcium chloride is equals to 1 by cation, which is cation. Ca plus 2 is cation and its valency 1 by valency. Cation valency is 2 and into lambda naught Ca plus 2 plus anion is a Cl minus, its valency is 1 by 1 right, 1 by 1 lambda naught Cl minus, that is equals to 1 by 2 into ionic conductance of Ca plus 2 value already is available 119 plus Ca plus 2 is 119 and Cl minus value is 76. If you do the simplification, again you will get same value 135.5 and its units are Simon centimeter square per equivalent. That's it. You can solve with the help of any method. It may be first method or second method, doesn't matter. In the first method, first we have calculated molar conductance and that molar conductance has converted into equivalent conductance. Here directly equivalent conductance only we have calculated by using 1 by valency into ionic conductance of cation plus 1 by valency into ionic conductance of anion, and of course infinite dilution only. That's it. Next question. Next question is like this. Calculate lambda naught ammonium hydroxide of the following data. Now we'll see the data. Lambda naught m per molar conductance of barium hydroxide is equals to 500 Simon centimeters per mole. Lambda m barium chloride is equals to 300 Simon centimeter square per mole. Lambda naught m ammonium chloride is equals to 120 Simon centimeter square per mole, and a lambda m naught ammonium hydroxide is question mark. That's it. First again we'll try to understand the given question carefully. Here calculate limiting molar conductance of ammonium hydroxide. Ammonium hydroxide is absolutely weak electrolyte. Already you know that weak electrolytes limiting molar conductance we cannot calculate from graphical method directly. We will calculate with the help of other strong electrolytes. Right. Here some other strong electrolytes data has given. Barium hydroxide limiting molar conductance has given, as well as barium chloride value given, as well as ammonium chloride value also given. With the help of these three values, we will find ammonium hydroxide value. Then for that purpose, we will arrange these three electrolytes in a systematic manner. That arrangement is like this. Answer: lambda naught ammonium hydroxide is equals to, right. How to arrange means ammonium hydroxide, if you split you will get NH4 plus and OH minus ions. Means first you have to select ammonium ion contained electrolyte. Ammonium ion contained electrolyte is nothing but ammonium chloride. That's why we will write lambda naught NH4Cl plus then OH minus ion contained electrolyte. OH minus ion contained electrolyte. Out of these three, OH minus ion contained electrolyte is a BaOH taken twice. Therefore, lambda naught barium hydroxide means NH4 plus OH minus, NH4 plus OH minus. But we don't want a BaCl. I mean BaCl related electrolyte BaCl2 will do the subtraction. BaCl2. Okay, right. But it is somewhat different than previous question. That is, here all are not having same valences. Ammonium chloride valency 1, here barium hydroxide valency is 2. That's why valences we have to make them equal. For that purpose, we'll do like this. Then this one and this one and this one, all three will just split. How will split? We'll just see then. Lambda naught ammonium hydroxide is equals to lambda naught NH4 plus lambda naught Cl minus plus lambda naught Ba plus 2 plus, then it is splitting as Ba plus 2 plus 2 OH minus, 2 OH minus. Therefore, we write 2 into lambda naught OH minus, again minus lambda naught Ba plus 2. How it is splitting Ba plus 2 plus 2 Cl minus. Therefore, minus 2 into lambda naught Cl minus. Here are similar terms will just cancel. That is a plus Ba plus 2 minus Ba plus 2. Next thing is, right, here thing is NH4 plus 1 mole lambda naught NH4 plus is there, and here 2 moles lambda naught OH minus ion is there. So I will just make it balance. Balancing purpose I am taking here 2. It is also 2. Means here we have to take here 2 to make the balancing. That's why now 2Cl minus plus 2Cl minus minus 2Cl minus cancelled. Then the remaining ions are 2 moles of lambda naught NH4 plus 2 moles of lambda naught OH minus, and we can write like this: 2 moles of lambda naught NH4 plus lambda naught OH minus also we can write. Therefore 2 into then otherwise we'll find directly then here. Anyhow, 2 moles of ammonium, its meaning is 2 moles of ammonium hydroxide value is obtained. Its ultimate meaning is 2 moles of ammonium hydroxide limiting molar conductance value is obtained. Okay, let's calculate first. I will calculate here, that is equals to all this value and this value and this value. If you substitute, you will get limiting molar conductance for 2 moles. We'll see then. Here 2 into, of course, 2 into ammonium chloride value is 120 plus barium hydroxide value. Barium hydroxide value is 500 minus barium chloride value is 300, and if you do the simplification, you will get 440. 440 units are Simon centimeter square per mole, but this is not our answer. That is not our answer. Is asking a limiting molar conductance of ammonium hydroxide. 1 mole ammonium hydroxide only asking, but we are getting here 2 moles ammonium hydroxide limiting molar conductance is obtained. Well, because here 2 moles of ammonium ions, 2 moles of hydroxide ions, nothing but 2 moles of ammonium hydroxide value is obtained. But we need for 1 mole ammonium hydroxide. That's why we will do like this. 2 moles ammonium hydroxide purpose, the value is 440. Then 1 mole ammonium hydroxide purpose, how much? 1 into 440 divided by 2. That is nothing but 220 Simon centimeter square per mole is our answer. That's it. Here, limiting molar conductance of weak electrolyte has asked, of course, and 3 strong electrolyte values has given, but here the valences are not same. That's why here I just multiplied with 2 to make the balancing. So 2 into lambda naught NH4Cl plus barium hydroxide minus barium chloride. If you simplify the values, you will get 440 Siemens centimeter square per mole is the limiting molar conductance of 2 moles of ammonium hydroxide. But we need for 1 mole of ammonium hydroxide. That purpose answer is 220. Right. Next, we'll see another question. Lambda naught m of H plus and CH3COO minus ions are 349.6 and 40.9 Simon centimeter square per mole respectively in 0.1 molar CH3COOH conductivity is found to be 1.55 into 10 to the power of minus 3 Simon per centimeter. Calculate a degree of dissociation. Calculate a degree of dissociation in 0.1 molar CH3COOH. The dissociation constant of CH3COOH. That's it. This is the question. Then here lambda m naught, nothing but ionic conductance, nothing but a molar conductance of H plus and acetate ions are given respected values, and in 0.1 molar acetic acid, of course. Conductivity is found to be 1.55 into 10 to minus 3. Nothing but a K value has given, and is asking the 2 questions. One is a degree of dissociation. Degree of dissociation is nothing but alpha value, and is also asking a dissociation constant, that is K value. Right, both will calculate. First will write answer, that is A, that is nothing but a degree of dissociation alpha. Alpha is equals to lambda mc by lambda m naught. This is our formula. Lambda mc by lambda m naught. Then here lambda mc, lambda m naught, whether available or not, we have to see that. Then we'll do one thing. Here lambda mc, nothing but molar conductance at a given concentration. and lambda m naught limiting molar conductance. First I will calculate limiting molar conductance of acetic acid. Lambda m naught CH3COOH is equals to lambda m naught CH3CO minus plus lambda m naught H plus. And if you substitute the values, H plus and acetate ions values, H plus value is 349.6 plus acetate ion value 40.9, and if you do a simplification you will get 390.2. Therefore lambda naught CH3COOH is equals to 390.2 Simon centimeter square per mole, means lambda m naught is obtained. Now we will go to lambda mc. Lambda mc purpose will use our regular molar conductance formula, that is a lambda mc is equals to K into 1000 divided by m. Why? Because at this concentration we are calculating, at this particular concentration, at this given concentration molar conductance we are calculating. That's why it is not a limiting molar conductance, it is nothing but a lambda mc only. Therefore K value is 1.55 into 10 to the power of minus 3 into 1000 divided by molarity is 0.1. Therefore if you do the simplification again you will get 15.5. Lambda mc is equals to 15.5 Simon centimeter square per mole. Lambda mc is available, lambda m naught is available. Therefore we'll calculate now alpha value by substituting both this value and this value. We'll see the lambda mc 15.5 divided by 390.2. Again if you do the simplification, alpha value is 0.0397. 0.0397 is alpha value. First question has completed. Then we'll go to second question, that is a dissociation constant. Dissociation constant I will find here only. B. Already you know the formula. K is equals to C alpha square by 1 minus alpha. In the last video we discussed about this dissociation constant formula based on Ostwald's dilution law, of course. And the C value, concentration value 0.1 into alpha value just now calculated 0.0397 whole square divided by 1 minus 0.0397. If you do the simplification value, then the final answer is 1.64 into 10 is to minus 4. 1.64 into 10 is to minus 4. This is dissociation constant. Of course, it is not conductivity, it is a dissociation constant value is obtained. Right. Okay. Here a degree of dissociation as well as a dissociation constant, both values we have calculated. Right. Next. Before we'll going to enter into batteries, again in some conductors some small concept is left. We'll just recall that concept, that is already known to you. Materials are classified into 4 categories based on their tendencies of conductivities. They are number one, of course, conductors. Number 1 are conductors. Number 2, insulators. Number 3, semiconductors. And number 4, superconductors. Therefore, in that first we'll see about conductors. Conductors, I think already in the last videos we have discussed regarding these conductors. Once again, just will recall. What are conductors? Means the substances which allows current to pass through them are of course conductors. Now as far as the solid conductors are considered, suppose examples are metals, alloys. Already we have taken as conductors. And of course not only metals and alloys, some non-metals also acts as conductors, like carbon black carbon black as well as graphite as well as some organic polymers also acts as conductors. Some polymers also acts as conductors. I'll repeat, not only metals, some non-metals like carbon black, graphite, some polymeric substances also acts as conductors. Next, second one is insulators. Insulators means like glass, ceramics will show very less conductivity. That's why they are called as insulators. Glass as well as ceramic materials. And the next one is semiconductors. Semiconductors conductivity is in between conductors as well as insulators. Semiconductors purpose will use examples like silicon as well as doped silicon as well as gallium arsenide. Gallium arsenide is also used as examples for semiconductors. Semiconductors conductivity range in between conductors as well as insulators. Next, finally, superconductors. Superconductors initially in the early stages only metals and alloys are used as superconductors at very low temperature, that is from 0 to 15 kelvins temperature. In the early stages only metals as well as alloys only used as superconductors at very low temperature. But in nowadays we are using ceramic materials, ceramics as well as some metal oxides, metal mixed oxides, some mixed oxides also using as superconductors at very high temperature, that is as above as 150 kelvins. Above 150 kelvins, ceramics as well as some mixed oxides also behaves as superconductors. I'll repeat once again. Materials are classified into 4 categories based on their conductivity tendencies. In that, one is conductors, insulators, semiconductors as well as superconductors. Conductors already we have learned in our previous videos. Then solid conductors, the best example metals as well as alloys. Now here not only metals, some non-metals also behaving like carbon black, graphite and some polymeric materials, polymers. And insulators. Insulators means some glass as well as ceramic materials conductivity is very low. That's why we will consider them as insulators. And semiconductors. Semiconductors conductivity range is in between conductors as well as insulators. And silicon, example silicon as well as doped silicon as well as gallium arsenide is using as examples. And finally superconductors. In the early stages, only metals as well as alloys only used as superconductors at a very less temperature, that is from 0 to 15 kelvins. But nowadays ceramics as well as mixed oxides also using as superconductors at 150 or its above temperature, 150 or above temperature, that is in kelvins of course. Alright. Next we have to start batteries. That batteries will continue in our next video. Thank you for watching. Right.